Let us start today's lecture with few problems based on electrostatics, and gradually I'll also take up few concepts which will elaborate mechanical concepts also. So let us take this first problem to understand how you approach. Take up B part of this question and let's see what the question is asking. The point is, in this problem we have two insulating hemispherical shells. If you observe, these are uniformly charged hemispherical shells and insulating in nature. Now, he has given that the uniform charge on this and this separately is capital Q, small q, and their radii are also given, r by 2. Question was simple. He said, what is the net electrostatic force exerted by each other? So in B part, can we think of these fundamentals, like how will you think of electrostatic or the Coulombic force magnitude between these two bodies, 1 and 2? So how do you think we should go about it? What should be the mechanism to find out the... If anybody wants to put up his idea, he can raise his hand. I'll listen to the idea and then I will share the method of solving the problem. And you can understand I have kept two problems together here. Like once I understand this concept, once a student understands this concept, he can definitely apply this concept in solving this problem also. And not only that, I mean, from the basics, again, we can solve this problem by another method also. So I'll discuss two methods in solving this problem, method 1, method 2. But just to build up the concept, like this problem is building up. It's like a build up of this problem. So the radii here are different, r and r by 2. And he wants me to find out the force. So I'll explain this problem to all of you. The problem is, if you start, like, you understand that you cannot solve this problem from absolute basic. I cannot find out electric field at all the points on the periphery of this hemisphere. That's not possible. Let's say I'm finding out force because of 1 on 2. To find out electric field at every point is not possible because of this hemisphere, because we are not on the line of symmetry. So we will solve this problem by an indirect approach. Now, that approach will make it a one-line problem. Now, let me explain how I think. First of all, what I will do is, by symmetry of the problem, I will say that I don't know the magnitude of force, but I am sure about the direction. Let's say, I say that 1 will apply a force on 2, which will be in the rightward direction. Let me call that F, and which will be acting along the line of symmetry. Now, how I said that? I said, take any ring on this hemisphere. Take any ring on the hemisphere. And because of a ring, you find out force on one of the particles, then there will be an anti-particle, an image particle. So if on one particle the force is like this, then on the image particle it will be like this. And then there is a circular symmetry. These vectors will be there on the complete ring, so the resultant will be rightward. And that holds for the second, the third, the fourth. So effective force is rightwards. That is very clear to all of us. The only problem at this stage is, I don't know the magnitude of this force, F, but I know this is rightwards. Fine. Now what I'll do is, I'll make a construction. I'll say here, let us assume that there is another hemispherical shell. Let us assume there is another hemispherical shell. And this guy is also having the same charge, capital Q. So if capital Q is there on the hemisphere and it is applying a force F, let us assume there is another guy which is symmetric to this guy, also carrying this capital Q. Now I have a complete sphere a hollow sphere having a total charge of 2 capital Q and uniformly distributed charge. Now I'm saying because of a uniform sphere, the field at every point inside the sphere is zero, shell theorem. So basically, the total force applied by this complete spherical shell on this hemisphere will be zero. Now, by principle of superposition, if this guy is applying a force F rightwards, this guy will apply the same force F leftwards on this hemisphere, because the total force by 1 and 3 on 2 is 0. So 1 applies F, this also applies F. F is still unknown. Now what? Now I will make more constructions. Now I'll say, fine. Let me draw another hypothetical hemisphere, hypothetical hemispherical shell, again carrying a charge of small q. And why I've made this? Now I'm saying, look into one and let's call this purple guy as F. It is also having small q. This is also having small q. All of them are insulating in nature. Now tell me, if 3 applies a force on 2 leftwards F, so by symmetry, mirror image symmetry, 1 will apply a force on F, which is again rightwards F. Think, if 3 applies a force on 2 leftward, which is F, this F, then 1 will apply a force on 4, which is rightwards F. That means 4 will also apply a force on 1, which is leftwards F. Now there are so many Fs here, and everybody is for a different interaction. Let me just follow up the chain. 1 applied a force on 2 rightward F. Then I completed this shell by another hypothetical guy 3. I said 1 and 3 will in total apply a force 0 on 2. So 3 applied a force F on 2 leftwards, right? Obviously, 2 also applied a force on 3, which is rightward F. I was not interested in this. Then I said, let me complete this inner spherical shell. Then I said, by symmetry between 2, 3, which is symmetric to 4, 1, if I complete this 4, 1 will apply a force on 4 rightward F. So 4 will apply on 1 leftward F. So now I have shown all the things in terms of F. Now I'm ready to solve the problem. I'll solve this problem in one line now. How? Finally, I will say that if you have a whole sphere, hollow sphere here, which comprises of 4 and 2, right? This guy carrying a charge of plus q, this guy, and 4 is also carrying a charge of plus small q. So plus small q on 4 and plus small q on 2. So the inner spherical shell is complete. And let me only take this hemispherical shell. Only one. Tell me, now if I tell you, what is the total force applied by the complete inner spherical shell on 1? So what will happen? 1 applied a force on 2, which was rightward F. So 2 will apply on 1, which is leftward F. Similarly, 1 applied a force on 4, which is rightward F. So 4 will apply on 1, which is leftward F. So basically, on 1, by this complete spherical shell, the total force is 2F. Finally, मैं क्या बोल रहा हूँ? That on 1, the total force by this spherical shell is 2F. And all of us know, if I want to find out the force because of a complete sphere, spherical shell, on any hemisphere, I can concentrate the charge at the center. What I'll do now is, in the next step, I will say that this hemisphere is intact and this guy gets replaced by a point charge. And that point charge is 2 small q. And now I have a hollow, uniform hemisphere carrying a charge of plus capital Q. And this 2q, 2 small q, is applying a total force on this hemisphere, which is leftward 2F. And how can I write this force now? Now I will use the concept of electrostatic pressure. Now I'll say, because of this 2q, if you look into this hemisphere, At every point, there's a uniform pressure because of this guy on this guy. So that uniform pressure multiplied by the projection area. If you want to find out the net force, you have to take the projection area. The projection area for this hemisphere, that is pi capital R square. And the only interest now is to write the expression of P, where I'll simply say, what is the expression of P? So P is the force per unit area on this hemisphere because of this 2Q. So that will be K into this charge 2Q.
It's insulating, so it won't conduct. So then you just have to put it all over the place and integrate that by
You
don't have to draw.
I think
it's fine. Cannot imagine
I'll request students to just mute themselves because there is So K into 2Q into the charge per unit area you can take and divide it by capital R square, and charge per unit area on this capital Q will be capital Q divided by the surface area, which is 2 pi capital R square. This is my expression of the pressure. So effectively now where we are heading, my answer to the question is F was required. So it is 1 by 2 times this expression, and that was pi R square multiplied by the pressure. And if you look into the pressure, I've written it as K into 2 small q into capital Q upon 2 pi capital R square divided by R square. Now you can open up the brackets and just write the answer, but the expression of the result will be the same. So finally, I got the value of F indirectly by completing the spherical shell. And I got,
The pressure part, could you just explain once?
How I got that? Fine. Actually, what I said is, once I concentrated this total charge 2Q at the center and I had some Q here, I can take example also. I can say if this person is having a charge, let's say Q1 is here, and this guy is having a uniform charge, which is Q2. How will we find out the force because of Q1 on Q2? So I said, you take any differential element on the surface, take any dA. So because of Q on dA, there will be a force which will be what? It will be the force per unit area, which I'm calling upon as pressure into the area dA. Now tell me if this is dA1. Similarly, there will be dA2, dA3, dA3, this force. Now basically, I've taken the resultant area vector because it seems that this guy, because when I will take the net force, I will take the vertical component. And let's say this angle is θ1. And basically, I need sigma upward, that is P, which is constant, into dA1 into cos θ1. And I'm saying pressure constant hai bahar aa gaya, sigma over dA1 cos θ1 type of terms. So I can call it θi, dAi, cos θi. So sigma over I, dAi cos θi is basically, if you look into the area vectors of a hemisphere, at every point area vector is dA, and its vertical component basically represents the shadow of this area on the base. This area is represented by this guy. So if I take a dA, the normal to dA is having an angle of θi with the vertical. So dAi cos θi is the shadow of that area on the base. And if I take shadows of all the areas, that becomes the total base area, which I said is the projection area, which is pi r square. If you want, I can integrate also, but it is not required.
Yes.
So that is how I got my expression. So fine. Now you people can open the bracket and write the answer. And simultaneously, we can think on this question. So what does the question say? Now this guy says that instead of taking a conducting sphere, he again took an insulator. He took 2 insulating hemispherical shells. So these are the 2 insulating bodies. He is having, the left guy is having a different distribution of charge, because it is an insulator, and the right guy is having different distribution, maybe higher or lower, whatever. So let's say this guy is having a small q over 2 pi r square and capital Q. Now the question is 1 and 2, how much force will these two exert on each other? That is a problem. Now, according to the previous problem, definitely I can solve this question, and then I leave it to you to solve it by that method, because the only difference is that this small q has been changed to, has been kept the same. The radius has been changed. And if you observe this solution carefully, yeah, Babu, you want to say something?
Yes, sir. So can we replace capital Q by capital Q plus small q by 2 and capital Q minus small q by 2? And similarly small q with the opposite state. And find the net forces to each.
Okay. Babu, tell me one thing. If you are applying this concept in this problem, do you think that result even depends upon this radius r by 2? And if not, now I'm just throwing a concept. If not, won't the answer be the same?
Yes, sir. It won't depend on the r by 2.
So if I am taking this illustration, I could have directly stated that whatever I have done in part 2, everything here, the only difference is that small q has been increased on radius up to r. So if a student analyzes this carefully, he will say, fine, sir, everything here and here is similar, only the radius is large. But technically speaking, the explanation is not depending upon this r by 2. So the guy who is making the problem is playing with that idea. He is just confusing us. We knew this thing, that the answer won't depend on it, and directly it will come out to be the same. Fine. Let's go to another method. If I don't want to apply this concept, because when I look into this problem, let's say if I'm solving this problem in exam, looking into this sphere, my mind starts thinking in terms of electrostatic pressure, because there is a very conventional problem. You give me a total charge capital Q on a sphere, and you ask me the force on a hemispherical part. So a student uses the concept of electrostatic pressure and gets the result, standard. Only difference is I changed the charges, and maybe this method was not known to me in the exam. Now I started to think, so what will I do? So now what I'm thinking is, let me just give you the thought process. So what I'm doing now is, I'm taking up a part and I'm using method 2. The question says capital Q, small q. I said, let me change the problem for my comfort. I'll say, just to ensure that symmetry comes in the problem, I'll say capital Q on this guy and capital Q on this guy both. If the charges were equal, let me give you the answer, which is simple for all of us, and then we will make appropriate changes. If the charge was equal, it was a body having a total charge of 2q. And if I said, tell me what is the force on this guy, F here, or 1 on 2, 2 on 1, F. So student will say, sir, fine, take electrostatic pressure and multiply it by the projection area. So pi r square into the term electrostatic pressure. And I think all of us can derive that term electrostatic pressure on the surface, because if you look into this body now, the sigma for this body is now 2q, and if the radius is capital R, it is 4 pi capital R square. This is my sigma, and this is the expression of the force on any one of them. And now only term is the electrostatic pressure. So can I directly say that electrostatic pressure is sigma square by 2 epsilon naught? You understand, if I take a differential sigma by 2 epsilon naught on both the sides, so remaining is also sigma by 2 epsilon naught, and then you understand how we get this term. So basically a student will say, fine, sir, I know the value of my answer in this question. Answer is pi r square into 1 upon 2 epsilon naught into sigma square, and sigma I got as q upon capital Q upon 2 pi r square the whole square. Let's say a student tells me this is the result. Now I'm making a direct statement. I said, if this is known to you, then for the given question, the only change you have to do is you write cap pi r square, you write 1 upon 2 epsilon naught. The only thing is capital Q square you replace by QQ and keep denominator as 2 pi r square the whole square. This is the final answer to part A by method 2. Now, why I did that? Instead, can somebody explain that this part was simple, like whatever I've done up to this point. I just took the same expression and only in the numerator, instead of capital Q square, I made QQ and I commented. Technically, we can comment that this is our final answer. And let me give the explanation to you. I am saying that if you look into this combination, think, but what you will do is you will go take any charge here, take any charge here, call it D, Q1, capital Q1, whatever, call it D small q. You will write a force between these two guys. There will be some vectorial interaction. Now, if instead of small q, capital Q comes here, the only difference will be in this charge. Other than that, the geometry, if you look into the expression of force, it is Kq1, Q2 upon r square. So this Q1 is same, distance is same, theta is same, force is same. Only thing is in the numerator in this vector, instead of D small q, there will be a D capital Q. The only difference in that D small q, D capital Q is the sigma of this sheet. It is the sigma of this sheet into dA. And in this, let me call it sigma 2. And in this dq, there will be some sigma 1 into dA1. Call it dA1, call it dA2. Tell me, if you write the expression in the new case, which I have drawn here, the distance is same, the dA is same, the angle is same, this sigma 1 is also same, only sigma 2 is different and sigma 2 is a constant. So if a lot of vectors are acting here and every vector multiplies by that constant only, the logic is simple. The resultant of vector will remain the same in direction. It will also get multiplied by the same constant. The property is if A1 vector plus A2 vector plus A2 vector is A net vector, and you multiply all the vectors by a constant, the resultant will also get multiplied by the same constant in the same direction. So that's what I did. I said, I will divide it by sigma 2 and multiply it by a new sigma. So I just replace sigma. And replacing sigma means replacing charge because area will remain the same. So I got the right to directly replace this Q square by QQ. Rest all the terms will remain the same along with the direction also. And that's why I got my answer very simply in a line. Just think what I said in this case. Think. I said, let me repeat what I did in A part. I'm not using the concept that I used previously. That can be used as we discussed. So I told let us solve it by another method. I said, if you give me total charge to capital Q and you say find out the force because of 1 on 2, I'll use the concept of electrostatic pressure into projection area. I'll get the force. I knew the formula of electrostatic pressure. I wrote it simply. I got my answer. Now what I'm trying to explain, as all of you are aware of this question, I'm just trying to add an idea that if he only changes capital Q by small q here, rest he keeps the same. Instead of capital Q square in the numerator, just write capital Q small q, rest will remain the same. Because if you look into all the possible interactions amongst the two bodies, every vector in this hypothetical situation and the actual situation is same in direction, in geometry. Only the numerator, there is a difference of dq, and dq is sigma into dA. So sigma is different. So I'm saying if I know this answer, I know that answer also. I'll just replace my final answer with the appropriate sigma. And sigma is charge upon area. Area is same in both the cases. So basically, I've replaced the charge. Somebody can say, sir, how do you interpret this? So this q square I was interpreting as qq. I thought one of q is coming because of this dq here, and the other is coming because of dq here. So in the second case, by the same logic, only the small charge will come and you will get the answer. So that is how we approach these two questions. All right. Let me go to another concept. Let's see how we approach. In this question, there is a cube made up of 6 thin insulating square faces. So what I'm doing is, I took an insulating box, a hollow, thin insulating cube, right? Now, on all the 6 faces, I have charge, which is given uniformly distributed. The edge length of the square is also given. The question is simple. Can we find out the electrostatic force on each face? So the question is like this. If I give you a cube, right, a hollow cube, with charges present on all the faces, by symmetry, on any of the face, the force will be same, electrostatic force. So that the question is, what is that electrostatic force acting on each face? Right? Now, let us take this charge as such. Now, he has said that each square side is having q. So let me say the total charge on this cube is 6q. Right? And every face is uniformly carrying a charge. Just to give a glimpse of distribution of charge, those faces will be hidden. So you'll see something of this sort and similarly something like this, right? Now, let us focus on any one of them, any one of the faces. Let me say that if this face experiences a force F, the question is, what is this? And let me mark it A, B, C, D. So on A, B, C, D, because of the remaining 5 faces, we want to find out the force. Now, I was very clear looking into the geometry of the problem that the force will be normal to the face. In case you are not getting that point, I'll justify also why I've taken the force to be normal to the face. But how should I think the problem? So let me explain the thought process. Now, a student says, sir, fine. If I have to calculate the force, I'll cut a differential element on the face. I'll find out the field because of remaining 5. And I'll take the vector sum. So a student marks it like this. His attention, his focus area is this face A, B, C, D. He cuts a differential element here. And he is thinking of finding out force on this small differential area. Let us call it DAI. So focus on ABCD and take DAI. Now I'm making a statement. The differential force on the ith element on the face ABCD should be written as the sigma. Basically, I'll write dq of that ith element and I multiply by the field E vector there. And if I can find out the sigma of all these, this is my answer. My answer is the resultant of all these forces. So that should be my answer. Now the complete thing is this. So student says, fine, sir, dq on the ith particle is sigma. Luckily, sigma throughout is constant. Even on this face, sigma is q upon d square. So that is known to me. I'll put sigma dai ei vector. Now forget sigma. Forget sigma. So sigma, this is gone. The series. Now differential dai ei vector, the net. This is what I'm expecting as my answer. Now the problem is, when I say field here, technically I have to write ei here because of the remaining 5 faces. So the problem area is you take a box, you are at a general location on one of the faces. And if you want to find out the net force, obviously remaining 5 can exert. That face itself will not exert any net force on the face. So I need field here because of the remaining 5 faces. So think of a box without this charged face, without this charged face. Think of a box. And then think of fields. Now this becomes complicated because calculating field because of the remaining 5 square faces at a general point on the 6th face is not simple, kind of impossible, even by integration. Then a student says, fine, sir, okay, I am not getting this. But then he says the direction, whatever is the field, if the field vector, let me use the symmetry. If the field vector here is at some angle, theta I with the normal to the face, theta, this is the normal to that face. So the student makes a comment, and I'll explain why I'm saying that. I'm making a comment. I'm saying the resultant of these guys will be sigma dai ei. I'm taking the mod of this field, and I'm taking cos theta I, and I'm saying now I'm commenting that this will be normal to that face, normal to the desired face, jiske upar we are calculating the force. Why I said that? Now think of symmetry of the problem. Think of symmetry. For every point which you are observing on this face, there is a mirror symmetric point lying somewhere else where the field will be the same and at a similar opposite angle with respect to the normal. So when you will take the resultant of these two vectors, the normal components will get added and the tangential will cancel out. So because I knew the symmetry, I said why to take the E vectors, only take the normal components of E and multiply it by the area, because force is going to be normal to the area. So I took only the normal component of the field here, because I knew that for every element there is an anti-element, the mirror symmetric element, having same field and symmetric direction in 3D with respect to the body diagonal face. Now at least the directions have become easy, because now it is sigma differential area dai, the field ei into cos theta I. And now I know the direction of force on this face. Now somehow I am searching. Remember, there is sigma over I also. There is sigma over I. I am searching how should I calculate this? Now, how should I calculate dai ei cos theta I? And now I got an idea that this term is the differential flux. So Gauss law comes into picture. This term becomes, so I used symmetry. Now I got the expression of the force in terms of some elements, and I'm saying this is sigma, summation over I d phi I. I'm denoting flux by phi. What is d phi I? D phi I represents the differential flux which will cross that small area because of the remaining 5 faces. So if now the flux is a scalar, so this becomes the total flux. Because of whom? So this is very important. We have to be careful here. This is flux on the desired face, on the 6th face, right? Because of the remaining 5 faces. Because of the remaining 5 faces now. Now the question in contention is, now the question changes. Now how my mind thinks is, I have got a box, I have got a face. On one face, because of 5 faces, how much flux will pass? So now I will use Gauss law and principle of superposition together in this problem. Now I will say, I'll use what? Gauss law and principle of superposition. I'll make some comments and then I will explain what I'm saying. I will say if all the 6 faces were present, then the total flux which will cross out of the box, just make a hypothetical surface just outside the cubical box. By Gauss law, the total flux is total charge upon epsilon naught, and total charge is 6q. So 6q upon epsilon naught is the total flux. And by symmetry of the 6 faces, out of every phase, 1/6 will come out. This is the flux which is coming out from the 6th phase. But this is because of all the 6 phases, and I need because of 5. So I have to subtract the contribution of that desired phase. And I said, if you take the desired phase as the last layer and try to wrap it in a piece of paper, like I have this book, think of this book like a face, thin face, and wrap it. So this dimension is not there. The thickness dimension, top, these 4 dimensions are not there. It's like a flat layer, and I wrap it. So again, by Gauss law, the flux which will come out will either come out from this side or that side, because these 4 areas tend to 0. And this guy, the 6th phase himself, is having a charge of q. So his flux from that side and this side is equal. And that is how much? That is q by 2 epsilon naught here, q by 2 epsilon naught here. So I said I'll subtract q by 2 epsilon naught. The contribution of the 6th phase in the flux. Obviously, I mean, answer is fine, but again, I have used another concept. Let me explain conceptually. I have used Gauss law. I have used principle of superposition, and I have also used a concept which is called upon as continuity of flux. Continuity of flux, yeah, continuity of electric field. Let me just explain these 3 concepts and let me apply again. There's a concept which says, if electric field lines are moving, then at any point, if there is a field, then the field, the left hand and the right hand limit of the field cannot change if there is no charge present there. So the electric field vector remains continuous at a point until and unless there is a charge coming at that point. If charge doesn't come suddenly, the field cannot change suddenly. And then there is another concept that if the distribution is not sudden, like in physics, there's a concept in mechanics which we call upon as jerk. There's something called upon as electrical jerk also. What is electrical jerk? If you bring a point charge suddenly at a point, it will generate an electrical jerk. And if you bring charge which is distributed in a solid sphere, then that is not a jerk, because charge is continuously coming in the form of dq, dq, dq. If charge comes and then vanishes, that is an electrical jerk. And I'm talking about a point charge. Now how I use this concept here. Think. I had 6 phases. I had to find out the flux because of remaining 5. So what was the picture in my mind? Picture in my mind was like this. I had a kind of a cavity here. I thought the picture is like this. I don't have anything here. And remaining all the phases, I have appropriate level of charges. Like everywhere I have all these charges. Now just think. I didn't have anything here, and I had to calculate the flux because of these 5 surfaces here. Now what I did is, I tried to calculate flux not on the surface. Basically, I'm calculating just outside the 6th phase. I'm calculating the flux, and then I will say whatever is the flux just outside, the same is on the surface, because the field is continuous, hence the flux is continuous. If I look into the effect because of 5 guys, this phase is not having any charge. So whatever is the flux because of 5 of them just outside, the same is the flux on the surface also, because that doesn't have any charge. And this is my answer, just outside because of 5. How come? Then when I had to calculate just outside, I introduced the 6th guy here. Then I said the total because of 6 is 6q upon epsilon naught, and I took 1 by 6. So out of the total, just outside this phase, this much flux is there. But this much flux also carries the contribution of this phase. And then I said, because of that specific phase, both the sides you have q by 2 epsilon naught, q by 2 epsilon naught. So I subtracted q by 2 epsilon naught because of this phase itself just outside. So just outside, I got the effect of the remaining phase. And then by principle of continuity, I said that whatever is just outside, that is on the face also, hence the answer. So my final answer now can be sigma into this term, and this comes out as q by epsilon naught minus q by 2 epsilon naught. So it is q by 2 epsilon naught into sigma. And to begin with, I wrote this, that sigma is charge upon area square. So it is q square upon 2 epsilon naught d square should be the result, because in the beginning itself, I wrote this term that sigma in this problem is q by d square. So that is how finally our answer to the question is q square upon 2 epsilon naught d square. And this is the problem. And we have used Gauss law, we have used continuity of flux and field, we have used principle of superposition to answer the respective question. Right. Avinash, yes, you want to say something? Yeah.
Alternatively, can I say that if I ignore the edge effects and think that all the sides which are touching the side which we are interested in, they will produce a E which is parallel. So the flux through them should be zero. The only side which is producing flux which is passing through the current side should be the one which is opposite to it. And that will produce a flux which is q by 2 epsilon naught.
Just a moment. Even let me just take your supposition. If I take the flux because of that side which is at a distance of d, how come can we say it is by 2 epsilon naught?
If edge effects are ignored.
Ignored. Okay. Then so you are trying to say that, I think what you are trying to say is, if you want to take this phase as such, and you want to talk about the interaction because of this phase on this phase. Now, if you want to write the flux because of this phase on this phase, and this guy is having a charge of q, now we can again use some symmetry to write the flux. Basically, one thing is for sure, Avinash, I think you are also saying that basically you want to write the flux. That is the point?
Yes.
Yeah. So one thing is for sure, that we are convinced on this thing that sigma into phi is fine for us. He is just explaining, Avinash is putting up a point, and that seems good to me. I'll just elaborate to all of you. He is saying that the flux that we are calculating, so what I have done, I have taken the net flux because of all 6 of them. Then I took the effect of the remaining 5 because I just came outside here and subtracted the effect of that guy. I got my tau. Now, Avinash, if you say the flux here because of remaining 5 is q by 2 epsilon naught, you have thought upon like from the top surface, the bottom surface, their effect, this surface, their effect. My only point is, are you trying to make the statement that top and bottom will cancel in flux and this will cancel? Is it what you are saying, if I'm getting right?
I'm saying that the electric field which are produced by the other sides would be parallel to the phase. So
Okay.
even flux is not cancelled, but no flux is generated, because the dot product will become zero.
Still, I'm saying if I take these two phases, let us take this phase as 1 and the phase on this side as 2. If I take 2 walls like this and we consider this wall, just tell me, I mean, wherever you go, you will have some contribution in flux because of this and because of this both.
If I assume that the electric fields are produced parallelly, then the dot product with area will become zero.
But still, I can see the flux. Like Like the top phase, in fact, what I'm thinking is, out of these 5, the 4 guys will have same contribution in flux.
Flux is being produced, but not in the direction which we are interested in.
No, but the matter of fact is, once you give me the area, flux we will only count in the area which is normal. Like if these are the 2 pages, 2 planes of my book, like this and like this, just think, this is 90. If this guy is charged and I want to write the flux at any point here, by standard definition, whatever field you will have, flux will be counted normal to that only, because tangential direction does not accumulate to the flux. So he will have some contribution for sure. And symmetrically, all those guys which are at 90 degree will have same contribution. So the only point which I get from your concept is that these 4 faces are symmetric. The top to this to this, the base to this to this. So this flux, a person can say, sir, I will see it as 4x plus y. I accept that point. X is same for 4 of them and y is different. This is the net I need, but this much I write. So if you can tell me because of any one of them, then I can complete my expression. I mean, this is what is correct. But you need to have some idea of, the question can be further generated. Like, you know the net, you know the flux because of one of them, then you can write because of remaining 4 of them, and all of them will contribute equally. That is how it is. I think you are feeling the field lines now because of plus. So when you look into this phase, every phase will have a unique pattern of field lines through that, and that pattern is symmetric. So that contribution is same. So 4 equal contributions, and the 5th one comes from that side, which is like divergent, like this. This guy will have a divergent pattern across this. And the total is this much. That is what we can say. So this question can be further framed into that direction. And he can ask me X value from this if I know Y. And Y again I can think, because if you look into flux because of this across this, then we can again start making symmetries. And I will use the Gauss law to generate the result. That is, I'll cut my piece of paper into 4 equal segments, and then I will generate a box. And out of box, I will look into one face, and then by symmetry, I will talk of one of them. So you got my point. We can go up to that point also. So this is how we can think in the problem. So we can initiate another problem. At least this idea can be written through that. Question is like this. Okay. Let us move on to the, Ved, you want to say something? Yeah.
Sir, in previous question, can we say electrostatic pressure as half sigma 1 sigma 2 by epsilon naught?
Yes. But the only thing is, you have to take insulating body then. Yeah. For hemispherical surfaces, insulating bodies, we can say that, because if it is a conductor, the complete problem will change, because the distribution conductor will govern on its own.
Yes, sir.
Yeah. So that is right. Let me take up another question. Now, this was quite straightforward. Once you understand that problem, just an application of 10 seconds. Just read the question, write answer. All of you can write it like just an application problem, nothing more. Application problem. Because they have given a point charge, they have given a sheet. They say this is a square side, this distance is d by 2, point charge is placed here. How much force will this charge exert on the sheet? A uniformly charged square insulating sheet. How much force will this guy exert? That was the question here. Just I will take this application and then we'll go to another mixed concept. Now, what happens here? By flux, I will just write the answer directly. You think about it, what I am saying. I will say you need to find out the force here. And that force will be equal to the sigma. So sigma is Q by D square into dA E cos theta, and that is the flux. And flux is basically Q by 6 epsilon naught. So this is the answer. So no need to integrate into lines and differential. You don't have to do that. Just observe what I have done and convince yourself. Here, this area and this guy on this area, downward F, or sheet ne charge pe upward F, that F will be equal to this. Can we say this? Just think.
Sir,
Yeah,
so
Arnav.
he's basically covering it, making it covered by a cube,
Yes,
then calculating on one side.
correct. Correct. That's what I have done. So I made a cube. Then I said the flux because of that point charge through one face is this much. And now I'm making a statement. The flux because of this guy from this, the field line patterns. इससे जो flux आएगा, if you just multiply the flux with the sigma of this sheet, you will get the normal force. Because force there is sigma of the sheet into differential area into EI into cos theta I normal sigma over I. And I just took sigma outside and I said this guy becomes the flux because of small q on capital Q. And flux I knew, so my answer is that. So very simple problem. Now, just I'll go to another conceptual.
Sir,
Yeah,
in the
Yeah.
previous problem, if in place of insulated we have conducting, so how can we approach, sir?
no. The complete essence. You are talking about this problem, the previous one. Not
This one, sir.
previous,
136.
this question itself, na? Yeah. This problem, na?
Yeah.
No,
Yes.
no. For conductors, you cannot apply the concept because there the distribution of charge is not known to us. For that, again, a new question will start. Because if you give me distribution, we can solve. If the distribution is not known, then we have to again use the concepts to find out distribution itself. And for that, we have few properties. As you must have solved a lot of questions that if there is a point charge, there is an infinite sheet, they will take systems where distribution can be calculated. Because what are the theoretical points we know? We know that above the conductor, the field is normal to the conductor. So the ideas that we have got is, in any question where conductor comes into picture, first of all, we will try to find out the distribution. You understand, answer depends upon sigma. And if sigma is not constant, I cannot take sigma outside. Then it becomes an integral problem. Then the complete idea is haywire because we have either we solve from the basic or this idea, the answer will remain the same. You have to integrate. And for sigma, only idea we have got is you presume something to be sigma there. Then what we do from indirect methods, we try to find out the normal component of field just above the surface. And then we say that that is equal to sigma upon epsilon naught n cap. And then we find out sigma. So that becomes an absolutely new problem. And for that problem, the first step will be how to find out sigma. And for sigma, you need to use principle of superposition to indirectly find out the field. Then sigma, then we can talk of the forces. So if you want to use the idea of flux, he has to give me one term as constant. Let's say these concepts can be used in multiple cases where they give you the distribution on their own. Uniform sigma is given. They give you the pattern of forces, and we utilize that to solve the problem. I think you must have solved those questions where if I give you a solid sphere, I don't know whether you have solved or not. A uniform solid sphere I give you, which is insulating. And I say I cut a slice inside the solid sphere at a distance of small r from the center. And somebody says, can you find out the force on all the charges which are present in the slice? You got my point, what I'm saying? I mean,
Yes, sir.
just, I think it is a standard problem of Hirodo. I don't remember whether it is there, but I roughly remember that that question is there in a standard book. That so basically every time there also they use the field function as rho r by 3 epsilon naught. They cut a differential element there. Then they say on that element there will be some rho into dv. dv they will cut into differential length which will be constant for the slice into dA. So what is happening there is rho is coming into length, small thickness, let's say t, then a differential area is coming. Anna? So this is what the charge is. Then a field will come and field is rho r by 3 epsilon naught. And then we'll say by symmetry, I need a cos theta term. I need a cos theta term. And then I will take a sigma. So if you remember in that question, my answer is direct. What I'll do is I'll have this rho square common. Every time I'll have what? Thickness is a common, 3 epsilon naught is a common. You understand that there is these terms are coming over there. We have a dA term, we have a r term, and we have this cos theta term. And the good thing is r cos theta at every point is actually the distance from the center, which is r, and sigma dA basically converts into area. So this becomes your answer. So when they say this, in this question, what I have done is, just to elaborate the same concept in this example, I have taken a uniformly charged solid sphere, uniformly charged insulating solid sphere, and I have cut a slice somewhere. And the thickness of this slice is t, and the distance from the center is r. And then I am trying to find out the force on this slice of charge, sheet of charge, net force. So what we are doing is, this is the field function, this is the cos theta term by symmetry, and this is the charge term. And the constants I have taken outside. And basically I'm saying that if you look into these terms carefully, like r cos, think in terms of flux. You will get the result. So for every dA, I took r cos theta as a constant itself. Because r cos theta everywhere, theta will change, r will change, but r cos theta will be a constant. And now my term will only be d. So I took the complete area. And the area can be written because this is capital R, this is small r. So I can find out the area of the sheet as pi into this radius is root of r square minus r, small r square, the whole square of that. So you will get the answer. Okay, let us carry on with the same here. Let me take a simple problem and then move forward. Okay. Let's take this question, the problem in consideration here. You have three very long, infinitely long, thin insulating rods. The linear charge density on each rod is uniform, and the three rods lie in the same plane and cross each other to make a general triangle. We are in a gravity-free space, let's say. So there is no other field other than the electrostatic field. So the question is, where can a point charge be placed so as to be in equilibrium? Let me explain how the question is. You take three long, thin rods. They are having uniform linear charge density, lambda coulomb per meter, that is given. And they are crossing each other randomly to form a triangle. This guy is saying that in that system, if there is no other field, I need to position an external charge somewhere to make sure that the charge remains in equilibrium. Where can you position that external charge is the question. So I'll make the diagram and then we can start. Yeah, Ved, you want to say something? Yeah.
Shouldn't it be centroids?
Centroid. Okay.
Because
how
of symmetry. Symmetry.
I mean, that is my contention. How can you elaborate on that symmetry? I mean, I want to understand like why that point. I am accepting your point because the first idea that comes to me also is a centroid. Let us draw that and let's understand how we make that comment. If these are three random rods, they're all infinite in length and they have lambdas over them, this triangle can be absolutely random. Anything. I mean, they just form a triangle, random. Lengths like L1, L2, L3.
They're in center.
In center. Okay. Now there are few things which are coming to our mind. Ved has said, Shashank is also coming up with a point, and like if all of us think in that direction, it comes to our mind that it can be in center, it can be centroid. So out of these points of symmetry, one thing is for sure, that answer is amongst them, like out of these points, it will be the result. Now, if we have, and obviously IIT will give you all the options there. And maybe a student can say, fine, sir, for a general triangle, for a symmetric triangle, these points are same. General, how will you justify? So let me justify this thing. How will we make a comment? So what I did, I randomly took a point P. I said, let me search for a point where the field is 0. Okay. So a student said, fine, sir, I dropped perpendiculars. I said the distance is R1, perpendicular distance. Perpendicular distance here is R2 and perpendicular distance here is R3. So we are searching for P such that the field at point P, because of these three, so let me call those fields. I know L1 की वजह से जो field होगा, that will be along this normal, call it E1 vector. Similarly, this is E3 vector along this normal, and this is E2 vector. We know because of an infinite line charge, field is along the norm. So field because of 1, field because of 2, and field because of 3, the three vectors are summing up to 0. The summation is 0. That I know. We also know that if lambda is given, E will be equal to 2k lambda upon R. It is lambda upon 2 pi epsilon naught R. So I know the value of E. So I know E1 is 2k lambda upon R1 and so on and so forth for E2 and E3. We also know that. Now, just observe. If you look into this triangle, let's say opposite to L1 if this angle is alpha, opposite to L2 if this angle is beta, opposite to L3 if this is gamma. For this random triangle, alpha, beta, gamma, by polygon law of vector addition, these three vectors will make a triangle. If E1 plus E2 plus E3 is 0, not only will they make a triangle, if I draw the triangle randomly, and then I'll say like this is E1, okay, this is E1, then randomly you got some E2, and then from the tip you have drawn a E3. If E1 plus E2 plus E3 is 0, this triangle will be formed. And now look into the angles. If angle between L2 and L3, this angle is alpha. Normal to L2, E2, and normal to L3, E3, I am saying this angle is alpha. Check. Lines are having at some angle, then their normals will also be at the same angle. Similarly, if I look into beta, beta is angle between L1 and L3. Their normal is E1 and E3. And E1 and E3 again, I'm getting this angle. And that angle there is beta. Check. Here beta is the angle between L1 and L3. And the normal to these two is E1 and E3. And similarly, I say this is gamma. if I look into this triangle and the triangle formed by normals, and the property that if two lines are at a given angle, the perpendiculars will also be at the same angle. The triangle given in the question and the triangle that we have formed are two similar triangles. So by similarity of triangles, I can say alpha ka L1 is to beta L2 is to gamma L3 should be equal to E1 is to E2 is to E3 because the triangle ABC and corresponding sides A ka beta, so call it C, B was gamma, call it D, and E. This I'm writing as triangle ABC and triangle CDE are similar. I got this, so I got this second condition. I knew that this property is known. I also knew this. I formed, by polygon law, I formed a triangle. That triangle was similar to the given triangle. The side lengths are different, but the ratio of lengths I got. And then I said E1 is to E2 is to E3. So basically, it is 1 by R1 is to 1 by R2 is to 1 by R3. Because 2k lambda is common in all of them. And now these statements tell me, now finally I can comment that if this relation we have got, I should be saying that area like L1 R1 is equal to L2 R2 is equal to L3 R3. So because of this, and now multiply this by half. And what is this half L1 R1 half L2 R2? Now you understand that this will come out to be a centroid because this is a point which divides this triangle into three equal areas. If you look into this area, the area of this triangle is half of L1 R1. Similarly, you can make a triangle here. Remember, that is not along E1 and E3. This is different. The area of this triangle is half of the base L2 into R2, and similarly this. So the three areas are equal. So a point inside the triangle which is dividing that area into three equal parts is the centroid. So hence it is centroid. Because of this, now I can say it is centroid. So it is a very unique geometry, and that is because of the pattern of field. अगर field का function 1 upon r का नहीं होता, तो ये L1 R1 equal नहीं होता, और तब फिर वो centroid नहीं. जैसे if I just want to make a comment, because Shashank also said that if they were finite rods, can you all tell me that if I just change this question, these were three infinite rods, so answer is centroid. If they would have been just a simple application, if they would have been finite rods, what would have been the answer? And why? Think. तो वो लॉजिक मैं सीधे दे सकता हूं कि अगर ये बंदे like just to put it that way, just an extension to my problem, I said, if you give me three finite rods, random, give me three finite rods, give me a triangle, they have random lengths L1, L2, L3, but lambda is constant. So if I am searching for a point in the plane of this triangle where the field is 0, let's say P, and EP vector I want to be 0, then directly I will say it is the in center. Now I leave it to all of you to think for a minute. Why I'm saying directly the center? Again, by proof. Like, I mean saying symmetry is something which needs to be justified through clearly. So we need to be clear on that. My proof is, if the field here is 0, first of all, what I'll do is I'll draw a circle taking center at this point. I'll justify by geometry. What happens is, if you draw a circle with this point as the in center, the radius, the perpendicular distance from all the three guys will be the same. Right? Now there is a property. There's a direct property. I'll prove it if you want. Property says the field because of AB line at P point is same as that of field because of the arc enclosed inside AB. I mean, if you draw these two lines like this, and you take this charge, this line AB, and I take this charge, जितना field AB वाली line generate करेगा P पे, उतना ही ये arc generate करेगा. I can prove by calculus why I'm saying this. Similarly, whatever this line BC will generate, I'll connect it here. I know the concept that the arc and the line, the arc enclosed by the line with respect to that point, arc का field और line का field same आता है. इसलिए इस arc का वही होगा जो इस line का होगा, इस arc का वही होगा जो इस line का होगा. Symmetrically, the third line will have the same field as the third arc. So basically the three arcs complete a circle, and inside a circle at the center the field is 0, hence the answer. Now why? The question is why a line can be converted into an arc. So it's a simple proof of a line. एक line में हो जाएगा. थोड़ा ध्यान से देखना. If this is our line, this is a general proof I am writing, just to recap your concepts. Generally, if I give you a rod and somebody says find out field at any point, any general point, not the perpendicular bisector, any general point P. So first of all, what the teacher does in the exam, teacher will do one thing. Teacher will just connect the endpoints with this point P. Then he will say ki, with respect to this point, taking the radius as R, draw a circle. Draw a circle. Then with respect to line BP and AP, whatever charge is inside this circle, just take that charge. And the field because of this charge is equal to this line. How come? So for that, take a differential dy, go to a general y, take a dy here. And the other student, what he will do? He will go to a general theta. Just look into this projection here. Projection here. At theta, draw a general d theta. Now this charge and this charge, just focus on, if I prove that field because of this and this is same, then next, hence proved. So because of this guy, if I write the field here, it is repulsive. And because of this guy also it is repulsive. So one of them will say it is k into lambda dy divided by the total distance, and total distance from this point to this point ka square. So I can write that in terms of theta also. This distance is r. Right? So that will be y square plus r square. And the other person will say because of this, the repulsive field will be, he will say k into charges lambda r d theta upon r square, because he will take this distance and this charge. Now just prove that these two expressions are equal. If these two are equal for every y and every theta, all the vectors are equal, so the net is also equal. Now check k and all this. Now just have to write theta in terms of y. So I'm saying my tan theta is coming as y by r. So just differentiate d by d theta. So secant square theta into r is dy by d theta. So dy can be written as r secant square theta d theta. Now check. This becomes k lambda dy. Dy is r secant square theta d theta divided by y square plus r square is this square. That is r square secant square theta. This complete length. And you can see here, it is k lambda d theta upon r. And you can see here also, this is k lambda d theta upon r. Hence proved that the fields are equal because of every dy. If it is equal for all the dy's, so the net is also equal. So in the exam, if you give me a line and you say find out the field here, I draw an arc. And for arc, why the field, writing field is simple? Because arc is a symmetric body. So for arc, I can use the angle bisector, all those properties that you know. Then it will be very simple. Line converted to arc. Karan, yes.
So will this concept also be applicable to magnetism?
If the only thing is, if you can justify that the nature of functions, because the problem can be that there the function is proportional to 1 upon r. I mean, generally, there are few concepts. When I use Ampere circuital law, there are some concepts. In fact, when we justify an Ampere circuital law, I use a similar concept there also. So yes, it is applicable in magnetism in a different form, but a similar concept is there also. यहाँ पर क्या हो जाता है कि once we get this ना, it becomes easy because I mean you get the point now, because of an arc at the center. If you know the total angle subtended at the center is 2 phi, so you know the direction directly along the bisector, and you also know the magnitude because you use the concept of projection length. So your answer will be k lambda by r square and whole into projection length, which is 2r sin phi. तो arc का field लिखना बहुत simple है. That gives you the answer. Okay, let me take up one concept here, possibly on this next page. Just a moment. Yeah, let's see how we think. One simple question let me take. This question I want all of you to think in case I have solved the sheet question or not. I'm not sure. Yeah, this is also very nicely explained question. In this question, not only am I interested in the answer, I want all of you to think about it and give me a proper explanation, because once I explain this, a lot of questions can be solved by the same concept. Just read it carefully and let us discuss it properly. Many a times I have heard this term that by symmetry, people say by dimensional analysis. That is all ridiculous, because there is nothing like dimensional analysis. There is a serious, clear concept how it is explained. So let me read, then take your viewpoints. There is a uniformly charged right-angled triangular lamina, ABC. Acute angle at the vertex A is theta. So 90 minus theta. The question is, if the potential because of this right angle triangle at point A is VA and point B, it is VB, can we find potential at C? And given, what is given in the problem? Given VA, given VB, given theta, these three things given, and obviously epsilon naught is a constant, that is no. Can you write VC in terms of this? Take a minute, just think. एक triangular sheet है जिसपे उसने uniformly, so sigma is constant but not given. Charge per unit area on the sheet is constant but not given. But the potential is given at A and B, and it is asked at point C. Now, how to go about thinking in this problem? One thing is for sure, I'm not going to cut the elements and integrate to write the function. That's not acceptable. That's not the concept, the idea behind the problem. Idea to solve this problem is like this. If I'll make some changes in the question, then I'll reach the concept. So like if this is A, this is C, this is B, he says this is 90. Do one thing. You drop a perpendicular from C and call this point as D, and then focus on these two triangles. Focus on these two triangles, ADC and DBC. Just focus on that. What I am trying to do is, I'll try to derive the potential because of this guy here, and I'll use principle of superposition. So body 1, body 2. So I'll write it as V1 plus V2 and get my answer. Now, I can directly write the expression and just go around the concept saying that by symmetry I've written. My interest is students think a bit and then, just explain properly how will you write V1 and how will you write V2. That is my interest. And if I can explain one of them properly, then obviously you will easily be writing these terms in such problems. So let me spend some time on this. Okay. So we are targeting how to write V1. So remove the other part and just focus on. Just give me a moment. Yeah. मैं ADC के बारे में explain कर देता हूँ. So ADC, this guy 90, this guy theta, and this guy 90 minus theta. Now I'm saying I need potential here at C, and that is V. That's what is required. Now do one thing. You draw this triangle again, like you take theta here, just rotate this triangle and make sure that you get corresponding sides, like AD ka corresponding, iska corresponding, and so on. So your 90 here was C, your theta here was A, and your 90 minus theta symmetric similar triangle was B. You knew that the potential because of this complete triangle here is VB. And I wanted V1 here. So you understand that I'm going to write something in terms of VB. Second thing was, if I know the lengths of these sides, like this is L, this is L cos, this is L sin. So I just converted the lengths, like AC was L cos, BC was L sin, and this guy was L. Here AC itself is L cos, this is L cos cos, L cos square, and this is L cos sin. So it seems that from this triangle to this triangle, they have multiplied every side by a cos theta. This is shrinked by a factor of cos theta, keeping sigma same. So there is a concept of zooming the area. They are zooming the area by a factor of cos theta. So all the sides are multiplied by cos theta, but the sigma has not shrunk. If you change sigma appropriately, then the answer changes. So एक चीज क्या है कि they keep the charge same and shrink it, then sigma will change. But this sigma and this sigma is same, so charge has changed. Now, the point is, how can I make a comment in terms of VB? Now, I'll go to a general explanation. Everything is symmetric. Sigma is same. Only the geometry has changed or zoomed. So how to tackle the geometry? So I am saying, beta, you take randomly two right angle triangles. Think like this. Now, thought process is, think like this. Randomly, if I give you something, and I want to write potential anywhere. Let's say you are discussing potential at a point. What you will do? If you take elements, what you will do? You will go to a x, you will cut a dx. Just think. Then you will go to a y, you will cut a dy. Then you will say, fine, sir, I have a small area, differential area, dx, sigma dx dy is my dq. Then I say, write the potential. So whether you write potential here, or you write potential here, or you write potential here, what you will say, you will write dv as k, dq. dq is sigma dx dy upon the distance. And these distances will be root of some x coordinate square and y coordinate square. Yeah, unke difference ka square. Now, what I'm saying is, from this triangle to this triangle, if you multiply by cos theta, every side, every x, every dx also. Mark my words. If you cut a x here and you go for a dx, if I cut a x here, I go for a dx, my x will multiply by the same factor cos theta, my dx, because like d of x, अगर x में कोई constant आ गया तो constant बाहर आ जाएगा, dx आ जाएगा. So x gets multiplied by a factor f, y gets multiplied by a factor f, dx gets multiplied by a factor. So dx में भी f का factor, y में भी f का factor. x में f का फैक्टर, x के डिफरेंस में भी f का फैक्टर, इसके स्क्वायर में f स्क्वायर का फैक्टर, इसके स्क्वायर में f स्क्वायर का फैक्टर, रूट से बाहर f का फैक्टर, f कैंसिल, so one factor of f, so answer is VB cos theta. VB cos theta. The contribution here because of this triangle ACD is VB cos theta. So what I have said is, and similarly you can do for the other person. मतलब यहां तो क्या हुआ, ADC का contribution at C is similar as contribution of ABC at B with a factor of cos theta. So my answer is, first I have written now. Now I can say this is VB cos theta. And similarly, the contribution of DBC at C, this angle is theta, is similar to contribution of ABC at A. So it is VA into, and the side 90 के सामने वाला side is L sin theta, and it was, so it is multiplied by theta. The answer to the question is this. This is the answer to the question. So what is the concept I have used in the problem? I have used this geometry. If one right angle triangle contribution at one point is known, another right angle triangle contribution at same point can be written if sigma is same, and it is similar triangle with all the sides, all the dx's, all the dy's, all the x, all the y's, everything gets multiplied by a factor of f. So answer will also get multiplied, you get the answer. So that is how you will get the answer to the question. Just think over this and then you can approach the question symmetrically. Right? One question I just want you to try on the same. You can use this concept here. It's just an application problem now. Just solve it. I'll give you a minute to answer. If a charge Q is uniformly spread on a thin dielectric square plate, the electric potential at the center of the plate is V1. If 6 such charged plates are joined to make a hollow cube, the potential at the center of the cube is V2. Then what is the potential at the vertex of that cube? What is the potential at the vertex of the cube? Students, I will have to leave here because I have another class in my CO batch. So I will have to rush for that class. Definitely in the next class, I will, you solve this question, get ready with your answer. I'll discuss this question there, but the concept is same to what I have done there. So whenever you use symmetry, now the symmetry that I have used there was on area. Similarly, I can go to volume type problems also. So I'll spend 10-15 minutes in the next class to just explain this, and I'll share the ideas. Take care of yourself, stay motivated for your JEE Advanced. And one small thing I want to say, please don't think too much about the mains result, even if you have got a very good rank or not a very good rank, because my 1.5 hour is over. So I'll take 2 minutes for you, all of you. That exam is an absolutely different ball game. The variety of questions will be different. So please don't spend any time there. Just focus on as many good problems as possible to get a great score in advance. That is our ultimate target. So please stay focused for 1 more month. Then you can enjoy your time. So wasting even a day or 2 days will not be good. God bless you. Take care. See you in the next class. Bye-bye, students.